This is the last part of Scala Debugging with Remote VisualVM. Parts 1 and 2 are also on YouTube. Part 1 is connecting up to a remote resource and using JMX and VisualVM. Part 2 is a survey of VisualVM and what you can get from it. And Part 3 is actually doing debugging of a Scala actor that has a race condition and is leaving garbage. And from the heap dump, we see the summary information about it, the threads at the time of the heap dump. Heap dump is a snapshot. It does a garbage collection, and what's left is recorded into this hprof file. And the things we care most about are the classes, the instances, which are none selected right now, and the query language, which is kind of cool. So classes is what we saw in the monitor, but this is post GC. And we see here the counts after GC sorted and with percentage and the number and how many bytes that corresponds to. We see data points. Podolsky data points are holding these date times and lists of data points. They have doubles inside them. So let's actually take a look at it. It's possible to query for those kinds of instances and see how many they are. We'll do that. We'll do a little bit of that. Well, let's grab one. Let's take. We're going to explore a little bit. It's going to be semi-structured, just to kind of get the feel of what the capabilities are. So let's grab a Podolsky time series data point, and let's show the instances of it. What it does in the instances view, we've now selected a particular class that created implicitly a query that groups by 500 instances at a time all of the instances. It does that just so you don't look at too many at once. And they're numbered from 1 to 500 or 499, and then 501 to 599. And if you look at one, this is a particular object in memory. It actually has the entire set of objects. And you see that the Podolsky this Podolsky time series data point has a timestamp, which is actually a date time. If we double click that, we'll see that its class name is org.jota time date time. And a value, which is a double. So it's basically a pair of date times and doubles, right? Mm-hmm. That is what this is. You can ask the question of any instance. So, and then it shows the references to it. And you can see that its reference is this : which is an immutable collection in Scala. We don't need this to take up space on the screen. So that's the : If we open it, surprise, surprise, the reference to it is the head, HD. The tail, if we focus on it, has another head value, which is a different data point, and tail, which is the next const cell. Using Lisp terminology, it's the next list element holder in the list, and it's a threaded list. Let's go back a couple of times, back to our data point. Picking any data point at random, number one is just as good as any. We can choose show the nearest GC root. What does that mean? It is when you do garbage collection, you start from roots, things that are findable as singleton or objects known to the virtual machine, and you do a mark sweep from those known roots outward, finding all the objects that are reachable, and anything that, and then when you're done with finding and marking all those, you then go back through and you delete all the ones that were not findable. So the roots are the points which are the starting point for garbage collection in. So we did a find nearest GC root. And this kind of walks outward from this object to all the references until it finds the shortest path to a GC root. So this random data point, instance number 3, its most immediate reference is the head pointer of a list. And if we walk back through the list, all the references back to the place where it's referenced, these are all the items in that list, we finally get to, and there's a lot in this list. There's quite a few in this list. Okay, there we go. We finally get to a sorted list object. I'm going to actually change the focus to that one just to get rid of all that junk we were looking at. So let's show that instance. In a sense, I just cut off all the things that were the list. Here's the time series that corresponded to. I'm going to re-look for its nearest root. You'll notice we don't see any of the TLs. Now we just see the sorted list that that data point was contained in. It's part of a time series, which itself is in a list that's referred to from a success object. Let's look at that success object. If we focus on it, I'm going to again reestablish the nearest GC root, just because it's the context we were following. That success object is of type Scala util success. We could look it up and see where it is. That's contained in a promise in a future, which is in a callback runnable, which is in a list of promises that's in a scheduler of actors that's in the light array revolver scheduler, this particular thing in Akka, the Akka scheduler. And eventually we get back to this abstract node queue.
Do not call me directly.
Akka. Right, do not call me directly.
So if you were to try to debug and find one specific object, could you? How do you search the instances to see?
Oh, you're so great.
Segment?
Search is done with OQL. So let's go the other direction. We just went upwards from an object to see where it was referenced and look at the classes and the types of things that refer to it. If we want to go the other direction and say from a given type.
So you can do that?
Yes. Use OQL. It's a JavaScript-based query language. Let's count the number of time series, for example. Let's say select and count objects which are on the heap whose type is a model Podolsky time series. We'll execute this query. We see there's 45 time series. Let's actually get a list of them. It's a slightly different one. Just select X from models Podolsky time series as name X. We were looking at those, and here's time series within Podolsky. We would know something about what these are. This is part of our debugging of an existing program. It's using a sorted list, and here is the time series. It's got an object with a sorted list with data points in it. If we take a look at the structure of this, there is something called time series, and time series has its ID, its data points. Each one of those is a data point, a possible aggregator. This is specific to Einstein. We were looking at data points with their timestamp and value, a date time and a double. Here's the corresponding Scala code for that object.
Can you show me again?
So you're tying it into the debugger and the inspector. They really represent, a pair of tools that we're working with. We can introspect the objects and see them. We go back to the code and we know something about the code in order to work with it. Okay, so let's list the time series, and you can look up the documentation for OQL. It's obviously Google searchable, but let me just assert that this is some examples, and I just learned by examples. Here is a list of them. Let's go to number 9. We saw it here in this inspect.
So you query for a certain set of them, and then.
Right.
But if you were looking for one specific one, I guess your query, arguably, you just
you make a more detailed query. There's a lot of stuff. I'm a novice at this, extreme novice. I used some examples, and they include.
Very humble now.
I'm very much a novice.
So many layers beyond.
You can,
I understand.
you can go you can go to the samples that they provide. They provide some samples. They provide samples here under permgen analysis and what have you. You can look at those. And I just copied and adapted a little bit of Cargo cult programming.
But see, the point here, I think the more important point is he probably didn't know a lot of this at the beginning of the exercise.
Nothing.
And he picked up a lot in a fairly short, that's the point to notice. So,
Right.
so don't go by the very humble presentation he's making. I don't know much, but you might want to focus on how fast he picked up.
Well, and the purpose of this is to help other people level up to be aware that it's possible and to have a path through the swamp that they could follow. Well, that is basically the idea. You can go forward and backward through the collections, work with the debugger, just a couple little things in terms of the success object. I wanted to list the success objects. This was something that, these are the success objects, that little piece of OQL for it. If we look at it, I was just looking them up. There were 7 of them. I could track whether they were appropriate. In fact, what I did on Einstein was to send a curl to it to shut down Einstein so it would no longer pull work. When it was quiescent, I sent the appropriate message to it to go quiescent. Then I got the heap dump. In fact, we would do that, but we could actually open an older heap dump. Let me see if I can open that heap dump very quickly. Let's grab the previous one. Let me grab the successes here. Yeah, here they are.
So what are those now? Those are successes that happen after you quieted everything?
Yeah, I'm gonna, they were actors which were still, they are the results that contain time series that were associated with actors which were stuck. And as the actors got more and more stuck, there were more and more time series.
Are you also going to show us how you found the issue in the code after you refreshed on it?
Well, once we knew that this was happening, then we could focus in on the places in the code where actors were the state machine of the actors. We could look at that. I think the time series handler.
Yeah, await.result was the pattern we're looking for, by the way.
Yes, await.result. So in time series worker, there was a timeout used here before, and it actually did an await result with a response here of wait time plus 5 seconds, and was not doing a try catch. And we changed it, instead of waiting 5 seconds to fail at the
wait time plus 5.
Yeah, this was actually a smell. The fact that it said add some slack for the timeout in process time series result. It turns out that the future that it's wrapping itself had a timeout and was protected and caught. But this await result, it was unusual. Maybe a GC comes along that takes 5 seconds or more than 5 seconds. And in that unlikely case, this one will fail first, and the success of the future time series result isn't reaped.
Okay, so you're spawning some actor there to do some work, and it has a
Right.
timeout, and the timeout is caught, and the other one is like left hanging or something.
So we added the comment here that process time series result already times out, so we use infinite to prevent an exception, because if you drill into this await result, you'll see that it throws timeout exception, and therefore that was causing this whole thing to throw an exception all the way up the chain of the way in which the actor worked.
See this line here? This is the good path, I believe. Am I correct, Fred?
Yeah, the sender was never getting the
I was
message,
never getting that message.
which caused the worker counts to be put back, the actors to be put back in the pool and to.
That's the leak.
So
then.
it was still waiting.
The exception happening on this line with that unlikely timeout under error conditions prevented the timer context from being stopped and the message being sent back to the
So
requester.
this was run within a try-catch, this piece of code.
This process time series result, that future, has a try-catch associated with it. Actually, we go inside of it, we would actually see that in fact it uses a future
First completed.
first completed of. So it's actually getting the timeout and catching it. It gets the timeout message and produces a failure as a result instead of a success. I think of it as a redundant fault. We tried to add another timeout and to protect a case, but there was a fault in that protection, which was a race condition. It's a race condition between the amount of time it takes for the underlying operations timeout, which did occur, but the other one, but something like a GC occurred in the middle, maybe it took 5 seconds. That timeout came along first in the series of processing.
And you only changed that to infinity and the case was closed?
Correct.
Oh, that's
Which
simple.
prevented, we could have done a try-catch, but that's paving the cow path.
Right.
Instead of fixing it, it's paving it over. It's like,
Yeah.
well, we got this timeout and that timeout. Oh, why? The other one is already has a timeout. Don't have a second timeout.
Yeah, just
Let it time out there and propagate the failure upwards. That's fine. The logic takes care of that.
And what is the result like? Was await.result? Is that like an async or synchronous call?
It's an asynchronous.
It's an asynchronous.
The await is the blocking call on the future.
Await is blocking.
Yeah, the await blocks on the future, but the future is the thing
so-
it's operating on is asynchronous. That's the point where you wait. Okay, so we're basically done. Any other questions?
This is interesting, helpful.
Yeah, I thought people might find something useful out of what we did.
Definitely, this is a great tool to be able to pinpoint a memory leak.
When I got done, I felt much more powerful afterwards than before.
Right.
Somebody had given me Thor's hammer.
Actually,
Good analogy.
this kind of debugging is actually a key skill that people need to have.
Yeah, it's usually when you like really need it and you really set yourself and learn it.
Okay, well, thanks. It went way over what I thought would be half an hour. This is the end of part 3 of Scala Debugging with Remote VisualVM. You can see the first 2 as well on YouTube. Thanks for listening.